This is EE300 Fall 2016, Module 1, Video 3, Laplace Transform Properties. In this video, we want to develop a number of Laplace transform properties. These will include the linearity property, the multiply by e to the minus at property, the delay property, the differentiation property, the integration property, the multiply by t property. We'll also summarize what we did, as well as take a look forward to the next video. Laplace transform properties. Previously, we applied the definition of the Laplace transform directly to find the Laplace transform corresponding to selected waveforms. It turns out that by developing a number of properties for the Laplace transform, what mathematicians would call theorems, we can generate new Laplace transforms from known ones. That's what we want to do in this video. This will quickly let us expand our inventory of waveforms we know the Laplace transform for. These properties have names that vary in detail from one author to another, but are fairly common across practitioners. Linearity. The first property is the linearity property of the Laplace transform. Since the Laplace transform operator is an integral operator, and since integration is a linear operation, it follows that the Laplace transform ought to be a linear operation. The details of this are as follows. An operator is linear if it obeys both scaling and addition. Scaling says that the Laplace transform of a scaled waveform is the scaled Laplace transform. We show this as a way to illustrate the general approach to demonstrating Laplace transform properties. We plug the waveform of interest into the Laplace transform and see what we can do with it. To find the Laplace transform of k times some waveform f of t, we plug k f of t into the Laplace integral. The factor of k comes out of the integral, leaving the definition of the Laplace transform of f of t. So the Laplace transform of k times f of t is k times cap f of s. Next, we show the addition property similarly. We plug f1 of t and plus f2 of t, the sum of the two waveforms, into the Laplace transform integral. We distribute e to the minus st across the sum and integrate each product separately to get the sum of the two Laplace transforms. Since we've already shown scaling, the general linearity property follows. The Laplace transform of a weighted sum of waveforms is the weighted sum of those waveforms' Laplace transforms. Let's explore an example, the sum of two exponentials. Suppose our f of t is e to the minus t plus e to the minus 2t for t greater than or equal to 0. We know the Laplace transform of each component will have a pole at that component's rate. What happens with the sum? First, we find the Laplace transform of each term, and using our knowledge that the Laplace transform of an exponential with rate minus alpha is 1 over s plus alpha. We then combine the terms by putting them over a common denominator, where we see that we will have a pole associated with each component exponential. We multiply out the denominator to get a polynomial of order 2, and we sum the terms in the numerator to get a first-order polynomial. Finally, we factor out the coefficient of s in the numerator to see the location of the 0 at s equals minus 3/2. Our f of s is a rational function in s, a ratio of polynomials in s. We can treat each polynomial as a sum of powers in s, or we can write it in factored form. F of s has poles at s equals minus 1 and s equals minus 2, the rates of the two exponentials making up f of t. The region of convergence where the Laplace integral is finite is to the right of the rightmost pole at s equals minus 1. F of s has one finite s0 plane at s equals minus 3/2. We can infer that when f of t is any linear combination of exponentials, including complex-valued exponentials, then cap f of s will be a rational function with as many poles as component exponential terms. There will be as many zeros as there are poles, although one or more of the zeros will be at infinity. The locations of the poles depends both on the component exponential rates and the weights with which the exponentials were added together, which means we can't make the kind of broad statements about the zeros of a Laplace transform the way we do about the poles and exponential rates. Here we show the poles and zeros of the sum on a pole zero diagram. The poles are at s equals minus 1 and minus 2, and the 0 at s equals minus 3/2. If we had chosen different amplitudes for the component waveforms, we'd have the same poles, but a different 0. We can use the linearity property to find the Laplace transform of f of t equals cos beta t for t greater than or equal to 0. Recognizing cos beta t is the real part of e to the j beta t, and using the fact that the real part of any complex value is 1/2 the sum of the value and its conjugate, we write that the Laplace transform of cos beta t is the Laplace transform of 1/2 the sum of e to the j beta t and e to the minus j beta t. We know the Laplace transform of e to the s naught t is 1 divided by s minus s naught, so our Laplace transform is 1/2 the sum of 1 over s minus j beta plus 1 over s plus j beta. Again, putting things over a common denominator and simplifying, we arrive at s over s squared plus beta squared as the Laplace transform of cos beta t. The Laplace transform for cos beta t has a pair of complex conjugate poles at plus and minus j beta and a 0 at the origin. The region of convergence of the Laplace integral is to the right of the j omega axis. Multiply by e to the minus alpha t property. Another property of the Laplace transform is the multiply by e to the minus alpha t property, sometimes called the S-domain translation property. Suppose we know the Laplace transform of f of t. Let's find the Laplace transform of e to the minus at times f of t. Plugging e to the minus at f of t into the Laplace integral, we can sum the exponentials of the product exponentials, sum the exponents of the product exponentials, and then recognize that this is just a definition of the Laplace transform, where s has been replaced by s plus a. Multiplying a time domain waveform by e to the minus at corresponds to shifting the Laplace transform, cap f of s, to the left when a is greater than 0 and to the right when a is less than 0. The region of convergence will correspondingly be shifted to the left or to the right. For example, we saw earlier that the Laplace transform of cos beta t is s over s squared plus beta squared. Using e to the minus alpha, multiplied by e to the minus at, the Laplace transform of e to the minus alpha t cos beta t is s plus alpha over quantity s plus alpha squared plus beta squared, whose region of convergence for the Laplace integral is real part of s greater than minus alpha. In the pole zero plot, the poles and zeros of cos beta t are shifted left from their original locations along the j omega axis to minus alpha plus j beta, plus minus j beta for the poles, and minus alpha for the zero. Delay property. Another useful property is the delay property, sometimes called the time domain translation property. If we know the Laplace transform of f of t, the delay property lets us find the Laplace transform of f of t minus cap t times u of t minus cap t, where cap t is greater than 0. Plugging into the Laplace integral, we realize that the integrand is 0 between 0 and cap t, and is f of t minus cap t for little t greater than or equal to 0, little t greater than or equal to cap t, because of the u of t minus cap t term. That lets us change the variable of integration and write the integral as being over 0 to infinity. E to the minus s cap t factors out, leaving us with the definition of the Laplace transform, even if the name of the integration variable is different. So the Laplace transform of f of t shifted by cap t is e to the minus s cap t, the Laplace times the Laplace transform of f of t. We had to multiply our shifted waveform by u of t minus cap t because we didn't use any information prior to t equals 0 in our Laplace transform. We see that when we delay in the time domain by cap t units, the Laplace transform gets multiplied by e to the minus s cap t. We can think of that as e to the minus s raised to the cap t power, and cap t is the amount of delay. Another useful property, here's an example. We previously found that the Laplace transform of the short rectangular pulse. Let's do this again, this time using the delay property. We can write the waveform, which is 1 between 0 and 1, and 0 everywhere else, as u of t minus 1. Laplace transforming each term in the difference, u of t goes to 1 over s, and u of t minus 1 goes to e to the minus s over s. We then combine everything over a common denominator to get the same answer we did previously. Seeing e to the minus s as e to the minus s raised to the first power, we identify the e to the minus s term going with the signal component delayed by 1 time unit. Differentiation property. The differentiation property lets us find the Laplace transform of the derivative of a waveform. Putting the derivative df of t by dt in the Laplace integral, we integrate by parts, letting u equals e to the minus st and dv equals df of t. When we evaluate e to the minus st f of t at t equals infinity, we know e to the minus st goes to 0 when s is in the region of convergence. When we evaluate e to the minus st f of t at t equals 0, e to the minus st is 1, and we get f of 0. The s from differentiating e to the minus st comes down and scales the resulting integral, which we recognize as the Laplace integral itself. So the Laplace transform of the derivative of a waveform is s times the Laplace transform of the waveform less the value of the waveform at t equals 0. The differentiation property is an essential tool in our use of Laplace transforms to solve differential equations. It introduces initial conditions into our calculations. In the homework, you'll find the Laplace transform of higher derivatives and see how the initial values of the waveform and its derivatives come into play. Later, when we want to go back to the differential equation from the relationship between inputs and outputs of circuits in the Laplace S domain, we'll take advantage of the fact that multiplying by S in the Laplace domain corresponds to differentiating in the time domain. Note that differentiation introduces a 0 at S equals 0. We can use a differentiation property to find the Laplace transform of sine beta t. The Laplace transform of the derivative of cos beta t is S times s over s squared plus beta squared, the Laplace transform of cos, minus 1, the value of the cosine at t equals 0. Putting everything over a common denominator and simplifying yields minus beta squared over s squared plus beta squared as the Laplace transform of the derivative of cos beta t. The Laplace transform of the derivative of cos beta t. When we differentiate cos beta t in time to yield minus beta sine beta t, and then take 1 minus beta out of the numerator of our Laplace transform, we see that the Laplace transform of sine beta t is beta over s squared plus beta squared. The poles of the Laplace transform of sine beta t are at plus and minus j beta, just like the poles of cos beta t. Since sine beta t is the imaginary part of e to the j beta t, it can be thought of as 1 over 2j times the difference of e to the j beta t and e to the minus j beta t, so it should have the same component exponentials as cosine does. Integration property. If we multiply by s when we differentiate in time, what do you think happens in the Laplace domain when we integrate in time? Consider the unilateral Laplace transform of an integral between 0 and time t of a waveform f with dummy variable of integration tau. We integrate by parts with u being the integrated waveform, whose derivative is the waveform itself, and dv being e to the minus st dt. When we evaluate the term in square brackets at t equals infinity, we know e to the minus st goes to 0 for s in the region of convergence. When we evaluate it at t equals 0, the integral is over 0 with and is equal to 0. We are left with 1 over s times the Laplace transform of f of t. Integration introduces a pole at the origin. For example, the ramp waveform, f of t equals t, can be seen as the area under the constant between 0 and t. As t increases, the area increases proportionally, so t is the integral of 1 between 0 and t. The Laplace transform of t is 1 over s times the Laplace transform of 1, which itself is 1 over s. The Laplace transform of t is 1 over s squared. We showed this previously by direct integration. Multiply by t property. If differentiating e to the minus st brings down an s in the Laplace integral, we can bring down a t by differentiating with respect to s. This is how we find the multiply by t property. Differentiating the entire Laplace integral with respect to s, we take the derivative into the integral and apply it to e to the minus st to pull down minus t. We recognize the integral as the negative of the Laplace transform of t f of t, so the Laplace transform of t f of t must be the negative of the derivative of f with respect to cap f with respect to s. As an example, let's find the transform of the parabolic waveform t squared. The Laplace transform of t for t greater than or equal to 0 was previously shown to be 1 over s squared. We take the negative of the derivative of 1 over s squared, which is minus 2 over s cubed itself, so the Laplace transform of t squared is 2 over s cubed. The Laplace transform of t had a double pole at s equals 0. The Laplace transform of t squared has a triple pole. The order of the pole increased by 1. We saw this previously when we went from the Laplace transform of 1, which was 1 over s, to the Laplace transform of t, which is 1 over s squared. Multiplying by t increases the order of existing poles. On the homework, you'll show that the Laplace transform of t times an exponential waveform increases the order of the pole at the exponential rate so that the Laplace transform of t e to the minus alpha t is 1 over s plus alpha squared. Summary. To summarize, in this video, we developed several well-known Laplace transform properties, including the linearity property, the multiply by e to the minus alpha t property, AT property, the delay property, the differentiation property, the integration property, and the multiply by t property. We also used the properties to expand our inventory of waveforms that we know the Laplace transform of, from the set shown on the left that we derived in the previous video to the ones shown on the right. Finally, we developed certain concepts along the lines of the pole location is the exponential rate. Using linearity, we saw that sums of waveforms introduce zeros into the Laplace transform. We saw that multiplying by an exponential of rate a shifted the Laplace transform by a. We saw that when we delay a waveform by cap t, the Laplace transform gets multiplied by e to the minus s to the cap t power, where cap t is the delay. We saw that when we differentiate in time, we multiply by s in the frequency domain, and that when we integrate in time, we divide by s. Lastly, we saw that when we multiply a waveform by t, we pick up another pole at the original pole locations. Next video. In the next video, we'll learn how to go back to the time domain from the s domain. That will involve discussing the uniqueness of the Laplace transform, reviewing how to write a rational function as a sum of partial fractions, and dealing with some special cases like complex conjugate poles, multiple order poles, and terms with powers of e to the minus s. This has been EE300 Fall 2016, Module 1, Video 3, Laplace Transform Properties.